Ladies and gentlemen, it's my great pleasure and honor to introduce the Intel HPC special keynote, and especially its distinguished speaker, I would like to say Mr. Computer Architecture, Raj Hazra. His topic today is Supercomputing Redefined, and will of course cover the new opportunities given through data-driven modeling. Raj is a perfect speaker for this subject, I can tell you, knowing him and cooperating with him for many years. Rajeeb Hazra is a corporate vice president in Intel's data center group and the general manager for the enterprise and government group responsible for all Intel data center business with enterprise and government customers. Raj has been with Intel for 23 years now, with technical and management leadership roles in Intel Labs and the Digital Enterprise Group. He holds a PhD in computer science from the College of William & Mary in Virginia. For his contributions, he has obtained the prestigious Intel Achievement Award. Prior to Intel, he was at Lockheed Corporation and 5 years at NASA's Langley Research Center in Hampton, Virginia. I could say much more about his achievements, but I would prefer to save time and to spare this time for the subject. So please welcome Mr. Computer Architecture, Raj Hazra.
The biggest challenge that we see in climate science is one around climate change. How will the climate change in the future, subject to various emission scenarios? Will extreme weather change in the future? Will storms become more common?
We're in an era where there is an enormous amount of potential discovery in cosmology. About 15 to 20 years ago, we discovered that the universe was expanding at an accelerated rate. We call this phenomenon dark energy, and we really don't understand what it is yet.
BP has to make significant breakthroughs in our understanding of the subsurface, especially under complex salt structures, for us to continue to grow our business.
5 years from now, we're going to have so much data coming in from new telescopes that are being constructed at the moment that we want to be able to keep up with that data and make discoveries in real time.
If I have a certain hypothesis that the jet stream is steering storms, and I'd like to be able to validate that hypothesis on hundreds of petabytes of data in a minute, would be game-changing.
Over the last 3 years, BP has made huge breakthroughs in our seismic algorithms that let us identify 1 billion barrels of potential reserves in the Gulf of Mexico. For us to be able to use new ideas and concepts like elastic wave propagation, we'll need more than 100 times the compute power we have today.
The state of the art in the Department of Energy is at about 25 kilometers. 5-10 years from now, a kilometer scale modeling will be possible. For an HPC system to be able to support running at those spatial resolutions, that's going to be quite a major undertaking.
As we look forward, currently a full waveform inversion project may take 2 to 4 weeks. We've got to let those projects happen in a matter of a day or two.
Good evening. Supercomputing redefined. That's what I hope to talk to you about today. If the time is any indication, there's no better time than to introduce this topic with a rate and pace of joint progress in the industry that we need to take on the tremendous opportunities from this redefinition. If you watch the video carefully, there was the obvious portion of HPC having redefined, truly redefined the mission. Whether it was a mission of science, you saw an oil and natural gas customer, and you heard how either there was a gain in the quality of science or the velocity of science, or more importantly, the impact of that science on human endeavor. If you listen even more carefully, what became apparent was the aspiration to do things that haven't been done before. Prabhat said it well. New techniques, new tools, armed in the golden age of data. That's what's driving us to this point of redefining two things at the same time. Supercomputing and supercomputers. The two go hand in hand. And today, I want to talk to you about the tremendous progress the industry has made, but more, perhaps, a glimpse of how we view this exciting age of redefinition as we go forward. So, as we talk about redefinition, and I know I've been in this room and other rooms before talking about what must change, energy efficiency, resiliency, programmability, all of those things stay true. But really what needs to change is to first look at what is the limiter to this redefinition, to realizing this tremendous aspiration that just a little bit of it you heard in the video from users. What is the limiter? What really is the limiter? Is it technology? Well, technology always can be better, and we in the industry work every day, every night to improve the quality of technology. But is it the true limiter in some sense? And I would pose to you that the true limiter is, or us. Don't read it as the United States, please. The limiter is us because the opportunity space, very much like that sky that we look at, is colored through the lens, in this case literally, by the tools we've mastered. The biggest tool is our human mind. It created the supercomputer, it created a bunch of other physical tools, but the biggest tool is the human mind. And has it reached its zenith of being able to analytically model things in the world and use this paradigm of using a model to simulate and predict outcomes? Are we limited by what we, over centuries and maybe millennia, have learned to understand? And if that is that little circle in the middle of the sky, then the rest of it is the world we haven't quite modeled through the lens of analytical tools. It's the world which is still out there. It is the world that's exposed through the veneer of data. So literally, the first objective we must have in this redefinition is to go to a new frontier. From the world of analytic models, where you have a model, you simulate using data, and you predict, to really a world which isn't constrained by a physical equation or a set of behaviors or a distribution function, but literally uses causality, context, and the knowledge of what task you're going to accomplish to create a model for that instance. It's really about initialize the state or the hypothesis or the framing of the problem, to increment it with data. And not just data, but as we'll talk about in a bit, its own execution towards finding the answer or generating the insight. And finally, with that, to steer, unconstrained by equations, in many cases, towards what it logically thinks is the right outcome, or at least the right set of outcomes with probabilities associated with it. So in many cases, removing this major barrier to really realizing the redefinition of the use of supercomputing lies in us freeing our minds from the constraints of analytical expression of the physical world to looking at data, learning to understand how data works, learning to understand what is in it as well as what's not in it, and then dealing with a whole new paradigm. If we look at it, what really happens is a change in the way we've approached supercomputing. What really happens is, other than the big change, is from moving from mimicking real systems through an analytical model lens to literally generating insight from things that may or may not be related at first blush to the phenomena that we are observing or we know of. If you look at this chart up, the data ingestion problem starts a whole new set of possibilities, which is really in the bottom row. We are very familiar with the top row, which is around modeling and then prediction through simulation. The bottom row opens up that rest of that sky, right? It is really about looking at data, looking at events, looking at self-optimizing, learning to look through that sky very quickly and efficiently, honing in on that next circle. And then, of course, not predicting, but inferring. Inferring insights that may or may not be useful, but nevertheless always taking insight forward. So with this in mind, and I know this is not a new concept, I do think that this is something we are all collectively working towards. The real question for us is, what happens to the world? As much as some of us live in the domain of high-performance infrastructure, down to very specific pieces of technology, whether it's hardware or software, what happens to this world that touches the use of supercomputing? Well, three things happen, but they're all codified in one word, or two words, excuse my math. Intelligent applications. Not applications that make us intelligent about a physical phenomena, but intelligent applications. There are three basic properties in our opinion. One is anomaly detection. No longer is this data-driven world the world of assured progress. You're converging, you're not converging, you're inbound or you're out of bound, right? You have a null situation, or you've reached some position on the graph. So detecting an anomalous situation, anomalous by the definition of the task you're doing, not just by some mathematical constraints, is key. The second is around efficient generalization. Once you learn from these applications learn from these anomalies detected, can you generalize it to a broader set of situations? Finally, taking that expanse a little bit further, can you autonomously adapt, that is, learn what needs to be changed in order for even broader set of situations and scenarios to be handled without explicit supervised training, right? That's the holy grail of intelligent applications, which is around continuous and autonomous learning. And both of those are important. The continuous is what gives us better and better fidelity and more impact from the application. The autonomous is what makes it tractable and practical in the world. So this, we believe, is the next future that we've kind of stepped into even today. The world of intelligent applications, which have these three fundamental properties of being able to detect its state against the task at hand. Number two, efficiently generalize so that that one action of an anomaly and its similar states can be avoided in the future, and then cross domains very rapidly. That is where the future of supercomputing is headed as it gets redefined in its use. So with that, of course, it's exciting to look at this kind of applications or this kind of attributes of applications and ask ourselves, what do we need to do? What do we need to do? And this isn't about just, in our minds, an additional 2x gigaflops per watt. This isn't in our mind just about handling, at the infrastructure software level, things like jitter and scale issues better, or constraining them better. This isn't about evolution. This isn't about evolution. It starts with the fundamental change of a new computational model. We believe when you transition from the world of using an analytic framework for every problem you solve to a data-centric framework, you have to have a new compute model. The second is around a new computing infrastructure around that analytic around that new compute model. And that's not just the architecture of a new system, it's architecture of the workflow and the tools necessary in order to actually have and manage such systems. And third, of course, is once you've done this, the new programming abstractions that make it possible to map these problems, the intelligent application problems, onto this computing infrastructure. So we think this is a time for a sea change, and we can see the bow waves coming. And in fact, many of us are in the process of driving them faster. In order for us to go into a little bit more depth, I like the fact that Herbode calls me Mr. Computer Architect, but then I would maintain to you that computer architecture is in real trouble. I want to get a real computer architect up here. Dr. Pradeep Dubey has been at Intel. He's an Intel fellow. He's in our Intel labs, and he is in charge of two things. And he'll always tell you I emphasize the second thing over the first. Build the future, bring it home today, right? So with that, I'm going to invite Pradeep up. I'm going to take my jacket off, if you allow me, because some of these lab guys don't do very well with business suits. So I'm going to leave it here. It's also pretty warm under the lights. So come on, Pradeep.
Thank you, Raj.
You actually bought a jacket.
I did. I learned something from you.
They never cease to surprise you, do they? So, Pradeep, we've been talking about new computation models, new computing infrastructure, new programming abstraction. Tell me, in this community, anything new means just greater amount of double precision flops, memory bandwidth, LinPack scores. Is this where we're headed? Because obviously, there's two parts of the world. One is the one we've known. The other is all around the data explosion and the cloud service providers and hyperscale players that seem to be focused not on that, but moving, storing, and doing something with data. Are these two paradigms in this new compute model kind of coming together? What's your view?
Yes, they are coming together, and they're actually coming together in a pretty transformative way. So, so far, when HPC folks around here, when we have used data, it's mostly been to validate an existing model, given by some god. And now we are moving to a paradigm enabled by data to actually be able to discover the model, quote unquote, reverse engineer the model entirely from data, right, where none exists, right? So it's not about validating a model of Higgs, the Higgs particle or some other gravitational theory, but new models altogether which didn't exist, and they're entirely being reverse engineered from data. And these low order approximations are good enough that you can actually use them for simulation and use them to build forward, and that's really truly exciting, right? Because it's going to transform the way we have never known this coupling of a data-driven plus simulation model.
So what you're really saying is, it's no longer just a simulation model. It's a learning model combined with a simulation model, right? So if this is becoming the new compute model, is this all that there's to it? Or are we forgetting some other attribute of brain-like or human-like behavior that's necessary for this to happen?
Yeah, so there's more to it. As the previous session was talking about, this augmentation of a neural network is already happening. And that's quote-unquote NN plus X. Mm-hmm. In this case, we're talking about NN plus simulation, right? But there's more to it. And the third element, which often doesn't get talked about, is and which we humans have, and what distinguishes as memory. And memory is essential, and so far memory has played a secondary to almost non-existent role in these hyped up deep neural network, but increasingly play a much more significant role. Not just the abstract model needs to be enhanced to have the ability to read, write, and store variables and learn from it. But we're seeing it increasingly in real use cases, large embeddings, sometimes like billions of items, and they all get stored, and they need to be kept in there. And so that memory, NN plus X plus memory, I believe completes the picture of the compute model abstraction that we're targeting.
I think I understood a bit of it. But from whatever I did, I think what you're really talking about is a compute model that I think, as someone who lives by selling compute, going to need a fair amount of high-performance computing, right? And that always makes me happy. But is it just the same kind of systems we build today, and that'll grow in size, and we're north of 100 petaflops today, and just going to 500 petaflops or an exaflop in 2021, or there'll be different kinds of systems?
Yeah, the serious significant system implications of this. The good thing is that the AI-driven supercomputing is not just asking for more and more flops. It actually, good news is it actually lends itself to delivering more and more flops. And that's inherent in the nature of AI. Because what it's trying to build, it's actually always trying to figure out that low-order approximation. So the models during training time, you have tons of data. Ultimately, when the model gets learned, it's very compact. Okay? And in fact, we hope that it's compact, because that's how we can deploy it at all kinds of edge locations, which are highly constrained in terms of compute and power that they can deal with. So, and it's not just a one-time learning and one-time deployment. There needs to be a constant feedback so that you can constantly refine the model and make it better and better. So there's a hierarchy of compute, and therefore it lends itself to that kind of deployment. On one hand, high supercomputing infrastructures, and other hand, resource-starved edge infrastructure.
Say a little bit more about that. I think we have some time. But before that, can I ask you a really hard question? Are you not hot under the lights with the jacket on?
Take it off?
Yes, please.
Okay. Okay, I always listen to you with any such guidance on life and business other than compute, yes.
That's a smart man.
So
my point is, talk to me a little bit about this notion of a hierarchy, right? Because clearly, some of us that live in the data center world think all of it happens in the data center, right? But this notion of being able to embed what you need to do in the compute model at different portions of both the data hierarchy and the processing hierarchy, what do you think it enables?
So it enables us, as I said, to actually deliver and meet this very fast-growing needs of compute for AI. Let's just zoom on into the data center or the supercomputer itself. So we first talked about this real-time loop from the edge to cloud. Now I'll just focus on the data center part itself, where the supercomputing flops will be delivered. The networking and communication needs, again, lend themselves to this hierarchical implementation. Let me be a little bit more precise. So imagine that you build a quote-unquote super node of some 64 nodes or 64 cards. Inside that super node, every node to node, card to card, has to deliver almost like hundreds of gigabytes of network bandwidth, inter node bandwidth for something like ResNets of today, even today, right? But when you actually encapsulate that as a super node, between super node, the needs are significantly less. You can actually use them commodity interconnect for between super nodes. So this communication is hierarchical. Within the super nodes, the injection bandwidth requirements are very high, and between nodes, between these super nodes, they're less. Okay, much more friendlier. So this kind of hierarchy that we see is increasingly seen both at the edge to cloud as well as inside the supercomputing infrastructure for communication and bandwidth needs.
So do you believe there is some notion of actually having uniform semantics at all levels of the hierarchy?
Yes, you can actually have a very uniform semantics for, you can abstract it at a much higher level. And I think that's where the significant opportunities lies for us to be able to abstract them higher so that we can actually create a much easier, friendlier, programmer-friendly semantics.
And that's kind of where I was headed. As you were describing all this complex architectures, I was thinking about my years of at least being associated with HPC programmers, where I saw two words come out of their mouths with anguish on their faces. One was parallelism. Okay, it's on your face too.
I know.
And number two was this need to get best performance, the need to actually co-design hardware and software, to be able to map the structure of the problem right down to the hardware that in the most optimized way executed it. So that means if you're a Ninja programmer or Ninja developer, very good news, or job, preservation. But for the rest of us, it's kind of the oh my God phenomena, right? So where do you stand on that in terms of this awesome capability being democratized?
Yeah, this is yet another disruption, right? That so far we were after trying to teach parallelism, trying to understand lowest levels, because otherwise you could not get quote-unquote performance. But now, in this world, we are, especially machine learning and graph analytics, you already see a move towards higher levels of abstraction. And that's helping, because when these neural networks are finally accomplishing a task, whether finding cats and dogs or some better approximation, the important thing to realize is that no one wrote a line of code, right? So the signal processing, image processing, the way we have taught is quote unquote coming to an end. And not only that, in fact, the recent work done, which actually shows a paper done with Professor Tim Kraska and Google folks, shows that machines can, on their own, learn basic data structures on their own, right, and adapt, whether it's octree, binary tree, whatever. So no one needs to go at the lowest level, like we have always gone and sometimes taken, felt good and were sweating as well. We don't need to do that, right? Machines can automatically learn these data structures and adapt to the real-time needs of the data depending on the
So what you really mean is this is the era where you don't have to program machines, machines program.
Yes. It's transformative in the sense that we are moving from, I believe, that we're moving from an era where we have spent a lot of time learning how to program a machine to machine programming itself. So from programming machine to machine programming, it's a huge disruption coming along our way. And we have been focusing on this in our research lab. We working with professors at MIT. We recently put on archive a paper called 3 Pillars of a Future Programming Model. And it has these 3 essential components. First one is intention-based programming, where the interface between human and computer changes dramatically to primarily expressing your intention and not learning a new language or going down to understanding the machine base, but machines coming to you at your level, and you can pretty much say, I need cars running on a racetrack at that intention abstraction. And then secondly, machines from those intentions will actually be inventing algorithms and data structures. That's the invention piece of it. And thirdly, not just a one-time thing, but increasingly as machine hardware changes or bugs show up and surface, they'll be adapting and fixing themselves. The 3 circle of intention, invention, and abstraction adaptation is what we consider as the 3 pillars of programming to come for machine programming.
You know, that's an interesting thought, this continuum that keeps things moving forward, right? Because I have often been asked the question, when is exascale? And the answer to that, if you're a strong type programmer, is a year. It's 2021, 2022, 2020. Pick your favorite level of either aggressive dreaming or hallucination, or whichever is your preference. But this one doesn't seem to have the answer to the typical question of when is this exciting future, because in many ways, this future is already here today.
Yes.
And it's only going to get deeper and deeper as we go along. Isn't that true?
Absolutely.
Is that your way of saying your job is done?
My job is just starting.
Okay, good. So I think before you go, though, and don't grab my jacket.
I was trying.
Okay. Before you go, I wanted to get your take on one final thing, right? We've heard a lot about HPC and AI convergence, right? That almost has this thing like fusion music or fusion, cuisine, where you bring together things and they lose their original identity or somehow have to trade off each other. What you're describing in this 3-pronged stool of a new compute model, a new set of infrastructure, and a structure of the infrastructure, and then a new abstraction for programming, this isn't really a convergence as it is a new class that supports both intrinsically, right? That there isn't the one has to adapt a little bit more to the other versus the other way around.
Yeah.
Is that true?
It's a new coexistence, a transformative way of looking at and viewing machines, and machines looking at you, and the two coexisting forever.
Okay. Well, always
Thank
good
you, Raj.
chatting with you.
Yes.
Nice jacket.
Thank you.
And remember, what was the second imperative? Make tomorrow happen today.
Today, yes.
Okay. So with that, thanks, Pradeep. I think even though in our limited time we kind of glossed over fundamental concepts, I'm touched by a few things that I remember, I realize on a daily basis as I go through this journey, following coattails of many smart people in the room and folks like Pradeep as well, which is society will change. Society will change in terms of the tasks we do because the role of computers and supercomputing in our lives will change to doing many of those tasks. We've often said, my children may be the last generation that ever learns to drive, right? I was the last generation that actually learned to write letters home. I know that for a fact because my kids don't write to me at all. But there's a societal change coming from this redefinition of supercomputing, which requires a redefinition of the infrastructure and supercomputers. And if that isn't an exciting time for us to be here, then I don't know what is. Typically, the perfect storm of data, the perfect storm of algorithms, and the perfect storm of physical hardware capabilities have never come together so quickly and so coherently in order for us to really pull in the tomorrow into today. And our goal at Intel is to work to do that, to redefine this landscape of supercomputing, to redefine our lives essentially through it, working together with the community at large, and being a part of it and making our contributions to it. So with that, it's always hard to compete with the evening gala, so I'll give you some time back, unless you have questions for me or Pradeep. If you ask me questions, I'll probably ask Pradeep to answer them. All right?
So you say that you claim that the machines will take over the programming, but then you have to ask yourself, how do you define the models that they will be using, and how do you even verify them?
I think you asked, let me give the answer, and then Pradeep will correct me, as he usually does and needs to. I think you asked two different questions. You asked, number one was what model they use. And in fact, this is a little bit like a programmer learning to be a parent of a teenager. It will probably go wrong, but you have to give them more and more rope versus going the other way, right? So in my perspective, you may not start with a model. It may be iterative. You may do progressive discipline, if that's a term you're familiar with in parenting, right? And that's the way the world's going to be, because in some sense, no one really knows the right answer till you arrive at the answer and you decide against a bunch of contextual information whether that's the right answer or not, or that's a plausible answer or not, right? This isn't, it's really what I term as graduating to the point of not asking your 5-year-old what 2 + 2 is, because obviously one of you knows the answer, the other one may not. It's really about participating in a research, in a PhD thesis with your child who's trying to figure out what the right answer is and may or may not prove it, right? I think the second part, which is how do you validate it, which is this big word I heard at the end of the last panel. It was something that's ended with "ity," right? What was it? Attestability or something like that. That is, I think, increasingly an interesting challenge. Not because some problem domains, I mean, once you have the right answer, it kind of did the right thing, you may not need it, but there are many business domains where that becomes an imperative for being able to deploy the technology, right? And so if you're purely scientists and engineers, we would probably not pay as much attention. If we wanted to actually be business people that moves this technology forward, we have to look at the various methods. Some are a compromise to performance, but that increase attestability of the methods, right? And I think that is where a fertile ground of research opens up.
No, you said it already. I'll just add to it. So the specification we're looking for at the intention level is the key, where we're looking at a new way of specifying programs and where the programmer interacts, and it's basically a domain expert or data scientist. So the intention captures quite a few things which make it easier for machine to generate code as well as be able to validate and verify. And in verification is a very hard problem, for example, right? And this is also where the simulation helps, because through simulation, many of these driving scenarios, we are able to actually have good enough models that we can actually simulate some of these anomalous scenarios without ever seeing them in real life. So the fact that we can adapt and we can actually simulate and synthetically create data sets and test sets, quote unquote, actually helps us much more than where we are today in terms of it makes the problem a little easier. But it's a different problem, it requires a different abstraction.
About it.
Are you telling us that Intel is transforming from a hardware company to a modeling and systems software company?
Intel transformed itself a few years ago from a chip company to a data company. And so, very simply put, if data is created, moved, stored, or processed, we believe there is a role for systems in it, and therefore a role for what we can contribute to it. So we are definitely no longer just a chip company, we are a data company. Thank you very much.